everyone. Now I'm going to present the topic formal verification of EIP 4844. And in my presentation, I will discuss the 3 questions and give you the answers to all of them. The first question is, why do we need to formally verify EIP 4844? And second, because this EIP is very complex and has a lot of components. So then which part of this EIP do we need to focus on? And the last question is about how we formally verify this parts. Before giving you more details, I would like to recall roll-ups. This diagram presents the architecture of the ecosystem when the EIP 4844 is implemented. And you can see that now user transactions are patched and sent to layer 2. And then layer 2 will execute the transactions, and these transactions with commitments and data block will be sent to layer 1. The proof verification of the transaction will happen at layer 1, and the transaction is only accepted if and only if the proof verification is successful. And the security of this approach is based on the cryptographic mechanism called KZC polynomial commitment scheme. My presentation is at a high level, and you don't need to understand the technical details of the stuff I show here to understand the rest of my presentation. And you can see that in the diagram, so the commitment scheme is very complex, and it's based on the knowledge of different areas like cryptography, polynomials, elliptic curves, and game theory. The only thing I want to focus here is that the correctness of this approach, this commitment scheme, is based on manual proofs. And it's good to have manual proofs. However, is it enough in our case? I'm afraid that the answer is no. So you can see on the slide, there are many systems with cryptographic mechanism. Their security were guaranteed with manual proofs, but later, different ways to attack the system were found. To eliminate the attack techniques and bugs in this system, formal verification has been applied. More interestingly, formal verification can find other issues in these systems. So that's why it's worthy to apply formal verification to the EIP 4844. However, there is one shortcoming with this approach. Formal verification is very time-consuming and requires a lot of efforts. Therefore, people usually apply formal verification to critical components instead of the whole system. So, in our case, the first question we have is, what are core components in EIP 4844? And here is my answer. You can see that there are 3 boxes on the slide, and each box is for one component. First, we have cryptographic libraries for the KGG commitment scheme. The next thing we have is the Python specifications for this EIP. And the last one is about the pseudocode of this commitment scheme. Okay, now let's go to the first component. So in this slide, I want to focus only on the GNAC. This is the cryptographic library for GKHNAC, and it is implemented in Go. And you can see that GNAC supports many constructions in GKHNAC, for example, road shifting, belong, or KZG. Moreover, GNAC supports many operations on different elliptic curves. You can see the list on the slide. And for GNAC, we want to verify 2 problems. The first thing is about the implementation of GNAC. This implementation is very complex because GNAC has a lot of optimization. And therefore, the implementation of GNAC looks different from the pseudocode. I mean, the pseudocode here is for some cryptography algorithm, for example. And we want to be sure that the implementation in GNAC is correct. And the next thing we want to do is to check some constraints on GNAC implementation. For example, here we want to check the pre and post conditions. And you can see the example here on the slide. We have a square root method. It takes x as an input and y as output. For this simplicity, I skip the body. And we want to prove that whenever this method is called, so the input must be greater than 0. Second, when we show that y squared is x. And how can we solve these problems? Our approach is based on the verification framework called Crypto. Crypto is a tool to reason about cryptography. And it can reason about the pre and post conditions. And moreover, Crypto supports refinement relationship. The refinement relation describes that two different programs can have the same behavior. So now I give you more detail. So from the pseudocode, we will transform it into a crypto specification. Let's go A. And then for the implementation in GNAC, we can automatically translate GNAC into crypto. And to ensure that GNAC is a correct implementation, we show that the specification B is a refinement of the specification A. Okay, now we go to the second component. The Python space for EIP for A44. Recall that the Python space describes the proof verification process in layer 1. However, these specs have a lot of modifications, and these modifications are for data structures in this EIP, and also some optimization related to the proof for a batch of transactions. So therefore, the Python specs look very different from the pseudocode. And you can see the link on the slide. This is for our Python specs. And we want to solve the problems related to the Python specs. The first thing is where the Python specs for the KGC by specification is a correct implementation of the pseudocode. Second, we want to show that the Python specifications for this EIP satisfy some properties. For example, after a block is finalized, the data blocks referred by the block are available for X weeks. Or note that we can start working on the second problem only if we finish the first step, because the Python specifications for the EIP for A44 include the KGG Python specifications. Okay, and now for this problem, we can use the Daphne. This is the verification framework to reason about program correctness. And our idea is that first, we manually translate the KGG pseudocode into a Daphne specification, let's say A, and then we translate the Python specifications to the Daphne specification, let's say B, and then we prove that B is a refinement of A. And to do that, we ensure that the KGG Python specifications are correct. Okay, now the next step is to reason about the properties of the Python specifications. So again, we encode the properties in Daphne, and then we translate the whole Python specification in Daphne. And we show that the Daphne specifications as now imply the Daphne property P. Okay, so now I'm going to the last component. The KGG commitment scheme is pseudocode. And we know that this commitment scheme is designed to satisfy the four following properties: correctness, polynomial binding, evaluation binding, and hiding. However, for the EIP 4844, we need to use the first three properties. The last one, hiding, is unnecessary. You don't need to understand the definition of these properties. The only thing I want to focus here is that the correctness, these properties are guaranteed by manual proof, and our target is to write mechanized proofs that can be double-checked by computers. Okay, so let's go to the first property of KGG commitment scheme, that is correctness. And verification of this property has two challenges. First, the proof requires a lot of underlying theories, and it contains a lot of writing steps. So you can see a table on the slide. This table demonstrates potential verification frameworks that we can use to verify this property. And here we have two tools, Cork, Daphne, Isabel, and Lynn. And we compare them based on four categories: the domain, impressionist, support libraries, and automatic reasoning. So let's look at the first line, Cork. And you can see that Cork is a generic proof assistant. This framework is very expressive and supports many libraries. However, it doesn't have many automatic reasoning techniques. In contrast, Daphne is a good automatic tool. However, it's less expressive than Cork, and it also supports less library. And Daphne focuses on only one specific domain, program correctness. Other tools, Isabel and Lynn, are generic proof assistant, and they have similar pros and cons with Cork. Now I'm going to discuss the verification for binding properties. Verification of these properties has two additional problems. First, these properties are probabilistic. Second, the proof for these properties are game-based. So to cope with these challenges, we extend our survey with an additional framework, EasyCrypt. This framework, EasyCrypt, is designed to reason about cryptography. It supports many automatic reasoning techniques, especially for probability properties. However, it is less expressive and supports less libraries. We are going to the end. In this presentation, I have presented the benefits that formal verification can bring to the EIP 4844. Moreover, I have identified the three components of this EIP that we should focus: the KCC cryptographic libraries, Python specifications, and the pseudocode of the KCC algorithm. I have also discussed challenges and potential solutions for verification of the core components. To reason about the correct implementation, we can use Crypto or Daphne. And to ensure the cryptographic properties, Crypto and EasyCrypt are good options. And to check program correctness, we can use Daphne. And if we think about general problems, then other verification frameworks like Cork, Isabel, or Lynn are worthy. And this is all for my presentation. Thank you for listening.